So today an RC oscillator restoration, Tesla BM365U. After restoring this one and this one, there's time for this one. It's basically a tube generator of sine wave signals from 25 Hz to 30 kHz. And of course this thing, the signal tracer, is also coming, but I want this one to be fixed first, because this one can be a useful tool when fixing this disaster. This RC oscillator is going to be simpler. It's in a much better condition. The previous owner was recently running it and it was working, so there's no point slowly reforming the electrolytic capacitors in it. I just want to preventively check the internals, show how it works, and maybe preventively replace some paper capacitors, check the ESR of the electrolytic ones, and check if the heater voltage is right, because in most cases the voltage is higher than it should be for the heaters. And this version BM365U is a bit different than BM365. For some other reason, the previous version was in a much smaller box, the same size as this one, and the next version is in a much bigger box. It does not have the voltage selector, 220 or 120 volts anymore, it's just for 220 volts. So we can explore what are the reasons for the bigger box, and I was lucky enough to get this piece, which was never opened before. It has this lamp indicating it's on, this potentiometer setting the level of the output voltage, with a switch, which surprisingly works. And these switches built into potentiometers typically are broken more often than not. You can tune the output frequency, and also set 4 ranges for the frequency, and 5 ranges for the output voltage. Up to 10 volts, 1 volt, 100 millivolts, 10 millivolts, or 1 millivolt. This is the ground for the output. This output goes just via the potentiometer, so it's always up to 10 volts. And this one goes via the attenuator. So the range can be anything from 1 millivolt all the way to 10 volts. And that's basically it. It seems in a good condition other than some details. This leather handle is falling apart a bit. Some scratches. This red mark here is faded. Fortunately the scale is not faded much here. But of course color paints are much more prone to fading than a black one. Especially orange and red tends to fade over time. But here it's still readable. The main thing is there are no botches in it. No botch repairs or modifications or missing parts. Which is very often much worse than if it's completely rusted and corroded and most of the components deteriorated. But now of course everybody's screaming, show the internals. And I actually got it still sealed. But it has to be opened. And the label says BM365U 220 volts 50 Hz. No longer the 120 volt option. 25 volt amps. Some adjustment potentiometer here and the input of the mains voltage. 0.2 amps fuse here. Let's check it. The actual one is 0.3 amps, at least not 1 amp or even 10 amps. Close enough, isn't it? But of course I will put the right one into it. One extra screw here in this one. And the back comes off, or at least it should. And that's it, the internals. Here you can see how almost half of the box is actually empty. In the previous version, the back of the box would be right against this chassis. The fuse holder and mains in connector would be sunken in this. This potentiometer here would have just a slot, no shaft. These would be just holes in the chassis for screws, not these pillars. And the mains voltage selector, 120 or 220 volts, would be here. And the back of the box was originally right against this, but now the hole for the selector is sunken deep inside of it. I'm not sure why the big box. Maybe they had a lot of boxes and wanted to use them, or to use the same box for more devices. Or maybe they decided to omit this voltage selector and the bigger box happens to have no hole for it here. But the most likely explanation is in the small box it was overheating. Especially with these 3 tubes here, concentrated in this small corner. When the back of the box was right against this, there was almost no space around them. So the later versions got the bigger box, the deeper one. Here you can see the power supply, the indicator lamp, the rectifier tube here, and the smoothing capacitor. Here's the box with the tuning capacitor, and in the oscillator 3 tubes here. 2 small tubes and 1 power tube for the output. This one is bigger. Let's remove the covers. The other 2 are smaller. There is another big electrolytic capacitor here. It basically removes the DC from the output signal and leaves just the AC. And here you can see the regulation lamps. The oscillator is actually using the lamps to regulate its amplitude, because the filament resistance goes up as it gets hotter. When the amplitude reaches a certain level, the filaments have a higher resistance, it reduces the gain or the amount of feedback in the oscillator and the amplitude goes no longer up. And some other components here, and some switches. Here's the attenuator with its resistors, I guess. Of course, this capacitor is sort of being baked next to the power tube, but in the bigger box, at least the heat has more space to escape. And you can see the entire chassis and the entire box is sort of universal. Here you can see a hole, which is not used. And this hole in the corner of the front panel, in the other ones, is used for the meters. And in this one, for this indicator tube. But now let's take a look at the bottom of it. And you're gonna see the potentiometer with the switch. Some resistors in the power supply. One more big electrolytic capacitor here. The tuning knob and its shaft. The frequency range switch here. The output terminals. The frequency range switch has a lot of resistors on it to choose from. Some trim pod here. This adjusts what's the maximum amplitude this one can set. And I guess this potentiometer adjusts the feedback. I guess this has to be adjusted. If it's too much, it's distorting. If it's too little feedback, the oscillations go out. This power resistor, the cathode resistor for the output tube. It's a cathode follower. A lot of smaller resistors here. And some paper capacitor in a poop resin, the brown one. A very infamous one. Of course, the sockets of the tubes here. Looking at it, there is really not that much to go wrong. The resistors are the newer style with the pins spot welded on them. Not the older ones with the pins riveted. Like these ones. These were sort of unstable. The resistance of these newer ones tends to be stable. Of course I have to check the electrolytic capacitors, but these tend to be good mostly. The worst disaster is this capacitor, the paper one in the brown resin, which I call the solidified poop. This one typically is deteriorated. This thing's about mid-70s, basically the end of the tube era. But it typically means most of the components are more reliable, except this type of paper capacitors. And this thing's already using the Soviet tubes here. The older versions were using Tesla tubes. This one is still Tesla. The rectifier's Tesla here. Here's the power tube. Tesla Czechoslovakia. A nice getter on it, not white. And the socket looks good. No damage here. Because way too often the tube is inserted such a way that the pin doesn't go between the contacts, but to the side. Sometimes it goes here. It typically still makes contact. A lot of these devices had the pins inserted wrong from the manufacturer and work to this day, but it's better to insert the tube properly into it. And these two, no damage here, no damage here, I'm lucky here. And this is the Soviet one, 6G1P EV, the newer version of it I guess, made in 73. And the other one which is 74. Here's the rectifier, nothing horrible here. This one is also Tesla Czechoslovak. I can see some darkening on it. Can you see that? Does it have so much use on it, or? It's actually possible this darkening happened when somebody turned it on after a very long time and it was rapidly reforming the capacitors in it. The glass typically darkens where there is a hole in the anode, and basically the material evaporated from the cathode ends up on the glass. The small tubes run at so little current I don't expect any darkening here. The power tube, also no darkening, so maybe this one was changed at some point, because virtually all the current going through the rectifier also goes through this one. Or maybe this capacitor rapidly reforming darkened this one. But of course if it's darkened a bit it doesn't mean it's bad, there can be a lot of life still left. Now let's check the electrolytic capacitors. First it's a good idea to check if there's any voltage on them. No voltage here, so let's measure if it's not shorted. It's charging, no short. And the one next to the power tube, charging, not shorted. And this one is tricky to test because the negative is not connected to the chassis. It can of course confuse you and you might be probing the negative probe to the chassis, which isn't actually connected to the negative of it. Here's the double capacitor in the power supply. One terminal, the other charging, no short. It's a double capacitor 20 plus 20 micro 350 volts. One section is 1.1 ohm, the other section 1.3 ohms. This is nice. Not bad for a 20 micro capacitor, 50 years old. This one is 50 micro 450 volts, 0.3 ohms, nice. And this one should be 100 micro. Of course the markings facing away from us, 0.16 ohms. That's really not bad. And nothing's leaking from the electrolytic capacitors, so I guess these should be still good. No need to replace them. Any other questionable capacitors? It's not easy to see, but this board has mostly resistors on it. One ceramic capacitor, tubular ceramic here in the center, and one probably polyester capacitor here in the center. These should be good, polyester and tubular ceramic. These don't deteriorate as paper capacitors. So now let's try to power it. If it was going to self-destruct, it would have already self-destructed. It was running recently. This cable is not original. Let's plug it in, turn it on. The lamp lighting up, nothing exploding. The transformer very slightly buzzing. And now these 4 lamps are not lighting up in operation. There's actually a very low voltage on them. These are 4 times 60 volts in a series. And oscilloscope time. Is it doing something? And the sine wave, nice. Changing the amplitude. This is the lowest range, I guess. It goes from 25 Hz, or even less, 21 Hz, the bottom of the lowest range, and the top of it, 159 Hz, nice. When I set 150, it's actually 143. It's a bit off, but anyway, not bad. 25 Hz, 24 point something, not bad. The second range, this should go from 150 Hz, 151, nice. It's quite close, all the way to 0.9 kHz. Actually quite close to 900 Hz. The third range, the top of it is 5 kHz, very close, and the bottom of it 0.9 kHz. Super close actually, that's virtually 900 Hz. And the highest range, this should go from 5.4 kHz, super close, to 30 kHz. 30 kHz. It actually goes a bit farther, all the way to 37 if you need. This seems like all 4 ranges are working here. It's a bit bouncy when I adjust it and then it settles. Maybe it actually needs to adjust the feedback. Or if I turn the potentiometer on the back, turning it up, distorting, this is what I expected. Turning it down, no signal. So this has to be adjusted, so it's a nice sine wave actually. Now it's working nicely. And adjusting the amplitude works well using this potentiometer. And the attenuator, well, this is a 100 times probe. Using this one just for case there is some high voltage getting to the output, so we can't see much at the lower ranges. Well, we can actually zoom it in. The highest one, second highest, third, this and this. This is 1 millivolt. The attenuator seems to work. And this one is before the attenuator. This one is not affecting it, just this one, so that's working as it should. But this indicator lamp is suspiciously dim. Is the heater voltage right? Or, well, it's actually using a different winding for the lamp than for the heater. Some are actually using the heater voltage for the lamp. The lamp is getting 5.5 volts, and this voltage is typically used in these ones for a 6 volt lamp. Let's actually check the lamp, taking it out without unplugging it, of course. It's actually a 12 volt lamp, 0.1 amps. It's supposed to be a 6 volt lamp. This is not original, it's sort of falling apart. Let's unplug it and take a look here what lamps we have. And this is 60 volts, 50 milliamps. That's the right lamp in it. Polam, made in 75. It seems to work right. No electrolytic capacitors hot. Let's actually give it the lamp it's supposed to have. Nice. Of course I should show it. 6 volts, 50 milliamps. Polamp 87. This one is going in and it's much brighter. Everything's working right. But of course I should preventively change this and... Also I should show the schematic, shouldn't I? This one is the old version with the voltage selector still here and these interference capacitors. Here is just a resistor, so you can't set how far this amplitude potentiometer goes. And here's the newer version. No interference capacitors, so there is nothing to explode in case they short. And no voltage selector here. And instead of a resistor there's a potentiometer here, so the maximum of this one can be adjusted. Other than that it's basically the same, except slightly different resistor values. These are still the old R10 series. This one is the new E12, E24, and these 6 F32 tubes replaced by some Soviet ones, which are basically equivalent. And the main basically goes in via a fuse and a switch. Here's the transformer, the lamp secondary, the heater secondary. The heaters are not actually grounded, they're connected to a voltage divider made of these resistors, probably to reduce the voltage between the heater and the cathode, especially in this one, which is a cathode follower. A cathode follower is basically a tube equivalent of an emitter follower with an NPN bipolar transistor. Here's the power supply with the rectifier, first resistor, first smoothing capacitor, another resistor, another capacitor for a less ripple. The supply voltage goes into here, powers the power tube, and this one being a cathode follower amplifies just the current, not the voltage. And these small tubes are basically an oscillator. The feedback from here goes back into the input. Here's a Wiener bridge with the tuning capacitor and a switch changing resistors for different ranges. Here's the potentiometer on the back of it, which basically adjusts the amount of the feedback, so it's enough to oscillate but not too much which would distort. And here are the lamps. And if the feedback is too much, the filaments get hotter, the resistance of them increases, and being in the cathode, it reduces the gain of this tube. So when the amplitude reaches a certain level, it no longer goes up. And here you can see the output is the ground. One output goes just via this potentiometer, and the other one via the potentiometer, and then the attenuator here. Of course I shifted it a bit. There is really not much to go wrong here. No exploding capacitors here anymore. These power supply capacitors I checked. This is an additional smoothing for these smaller tubes. And this 100 microelectrolytic capacitor blocks the DC portion of the signal and passes just the DAC to the output and to the feedback. And the old marking for 100 micro is G1. The old marking for 10 nano is 10K. This is a polyester capacitor, and this one is ceramic. These are not problematic. These tuning capacitors are air capacitors. Nothing really to go wrong. Maybe some contact cleaner for the switches. You have to check the heater voltage, and the main thing is this capacitor 100 nano. M1 in the old marking, which is a paper capacitor. And if it shorts or has a leakage current, it basically brings a positive voltage into the first grid of this tube, which could damage it or at least make it not work. The first grid shouldn't have a positive voltage on it. The voltage should be negative in reference to the cathode. Of course, the cathode is lifted by several volts because there is this series cathode resistor. And this capacitor should be definitely preventively changed. That's this one here. It's actually mounted using this band. And that's it. Visually it doesn't look that bad actually, but you never know with these paper capacitors. It's starting to form a crack here, doesn't it? I'm not putting it back. 130 something nano, that's off by about 30%. And this one is 96.5 nano, just 3.5% off. Now let's measure the leakage current of the old one at 325 volts, the rectified mains. And it charges and no leakage current almost. It goes down less than a microamp. This actually surprises me. I was expecting it to be quite leaky. And the other one, the new one, again it charges and no leakage current. And of course now let's keep the capacitors charged to rectify the mains voltage, so you get a shock. Just kidding, let's discharge them using the lamp. Let's test these on my ring tester. The old one, 14 rings. This is basically as good as a paper capacitor can get. This is not bad actually. The new one, it's polyester, 19 rings, typical for a polyester capacitor on my ring tester. Just for comparison, a ceramic 100 nano capacitor makes just 7 rings, and a polypropylene 100 nano capacitor, 75 rings. These are all 100 nano capacitors, as there is a massive difference in the dissipation factor. The lower the dissipation factor, the more rings. So of course the polypropylene capacitor is the best, but a polyester capacitor is definitely enough to replace a paper capacitor. This handle could be probably sewn back together. It's 2 layers of leather and this metal band, a steel band in between. Putting the new capacitor in. This capacitor is soldered in, and there is a tiny capacitor, and one pin of it actually fell off somewhere. And of course, for it to be interesting, the capacitor is not in the schematic. One pin of it goes to the grid, the first grid of this tube, which is here on the socket, and the other one probably was somewhere here. It seems like it was the anode. It makes no sense for it to go to the heater or the second grid. I guess it was here, and basically reducing the bandwidth and preventing some high-frequency parasitic oscillations in it. And this thing appears to be something like 10 or 12 picofarads. The solder joint is fixed. And now testing time, and let's monitor the current draw from mains, plugging it in. The tubes are warming up, the resistance of the heaters goes up. And now it's starting to run. It's at 225 Hz, 150 Hz. With the capacitor replaced, it might actually be a bit more accurate. 150 Hz at the beginning of the second range. And this is the heater voltage, which is a bit excessive. Should be 6.3. but I can't add any extra turns on the primary. And this section in the schematic is not there, or at least I can't find this terminal going to it. So it's probably just a simple winding with 2 terminals. So the only way to reduce the secondary voltage is putting a resistor in series here. Of course, this being made for 220 volts, and now the nominal mains voltage being 230 volts, also contributes to the excessive heater voltage. That's the total heater current. That's the difference between the nominal heater voltage and the actual one, 0.53 volts. Calculating the series resistor, we have to drop this voltage on the resistor as this current, so the resistor should be 0.37 ohms. Just playing with the oscilloscope, the frequency on the dial is set to 10 kHz, and the amplitude at maximum should be 10 volts RMS, which it is now. And some FFT is this the third harmonic, this is the base frequency. Of course, when you set the amplitude too much, some more harmonics pop up here, and turning it down, some of the harmonics disappear. Even though, of course, on this oscilloscope the FFT isn't that advanced. Let's turn it up. Now the harmonics appear here. Turning it down, they disappear. I'm not sure if I'm using it right, but there are basically no settings for the FFT. And of course, let's zoom it in and you can see the distortion when it's too much. The potentiometer on the back. Let's just check the resistances of these resistors for the range selector. These are critical for the accuracy of the frequency. And the lowest range seems to be a bit off, the other ones are quite accurate. The highest range is using these 56 kilo ohm resistors, which are quite close. The second highest is using weird values, 348 nominal kilo ohms. This is also very close, about 1% off. The second range is using 2 mega ohm resistors, super accurate. And the lowest range is using some series combination of more resistors. These are supposed to be 5.1 mega ohms. And this one as well. This explains why the frequency is a bit lower than it should be in the lowest range. A higher resistance makes the oscillator slower. But I'm going to leave it as it is. It's about 1% for the 3 upper ranges and 3% for the lowest range. Some contact cleaner into the potentiometers and the range switch. I disconnected one of the terminals of the heater winding, and let's measure the actual heater current and the inrush when I turn it on. Let's see. The inrush. And it's going down. That's about what I've calculated. Putting 3 1 ohm resistors in parallel in a series with the heater winding to reduce the heater voltage a bit. Now it's much closer to the nominal 6.3 volt heater voltage as the nominal mains voltage 230 volts. If anybody's curious, the first smoothing capacitor voltage is 265 volts, the second smoothing capacitor 247 volts, and the third smoothing capacitor for the small tubes 160 something volts. The first, second and third one. The first capacitor ripple, not that bad, it doesn't seem to be rotten. But nothing's actually powered from the first capacitor. Everything's powered from the second or third one, and on the second one already no visible ripple, giving it the right 200 mA fuse or 0.2 amps. I was going to say the restoration is finished and it stopped working. What the hell? I was thinking I put a bad fuse into it, but actually, when I was putting the heater series resistor in place, I had to unscrew the power supply module with the transformer and this metal, and as I was moving the transformer, the wires going from it to the switch in the potentiometer, I moved them and one of them actually came off here. That's it. Pulling the wire, it actually came from the eyelet. I guess it was a bad solder joint from the manufacturer, which I discovered now. And of course, the insulation on this mains inner wire is falling apart. Fortunately, the other wires have a good insulation on them. Okay, the wires are replaced here. Okay, now let's call it working. Now it's finally ready to be reassembled. This handle is sewn back together. I didn't do it, ladies are much better at this. I could change the resistors in the Wiener bridge, or Wiener bridge actually. I guess he was German, but I prefer to keep it more original. I want it working and reliable, but I don't want to change more components than necessary. A 3% error in the lowest range is acceptable, and if I ever change my mind, I can just change 2 resistors here and that's it. So that's it back in the box, and of course this is a much more appropriate oscilloscope to show the waveform. Another bloody long video, which was also laborious to make. So really please consider subscribing, supporting my channel on Patreon or using the thanks button, based on how much you've learned from my videos. And big thanks to all of you who already support me. You really keep this niche channel possible.